Hello, everyone. My name is Burkan from Oregon State University in the United States. I'm very happy to be here with you today, giving this presentation. I have been a big fan of the Rock Talk series of Rilem. Therefore, this is an honor for me. Thank you for joining me today. I have two main objectives in this presentation today. First, I would like to cover the progress that has been made by a number of researchers, including my research group, over the past decades with respect to the passivity and chloride-induced corrosion of steel and concrete. In doing so, I also would like to demonstrate the process of bridging length scales from atomistic to macro scale through the synergistic use of computational experimental methods. If you look at the literature on research on rebar corrosion in concrete, you will see that in the last 3 decades, we have seen an exponential increase in the number of papers, publications, and corresponding citations. This significant increase coincides, the onset of the significant increase coincides with the publication of Tutti's 1982 paper, which basically described the reinforcement corrosion problem in concrete as 2 independent stages separated by a distinct event, which is basically corrosion initiation. With respect to this 2-stage approach, the idea is that in the initiation stage, aggressive species like chlorides or carbonation penetrate through the concrete cover towards the reinforcement, and they start accumulating around the reinforcement. However, corrosion does not initiate because the amount of chloride, for example, at the rebar level has not reached the level to initiate corrosion yet. The initiation of corrosion is defined by the exceeding of the chloride content beyond a critical chloride threshold. And after this point, the propagation stage is defined. And during the propagation stage, we assume the corrosion has initiated, active corrosion has initiated. The 2-stage approach, as I described here, relies on the definition of a critical chloride threshold. However, this concept has been quite elusive in the sense that as we try to measure this quantity using different approaches, we actually see that the variability that we obtain from the reported chloride threshold values is getting larger and larger. This plot shows over the decades how the variability in chloride thresholds change, and you can see that this variability is always increasing. So it is not an easy concept to define chloride threshold, and there are many reasons behind it. There is a very good paper prepared by Rilem Steel Concrete Interface Committee that identifies a number of critical aspects of the sources of this variability. And I highly encourage you to have a look at this paper to better understand why we see this ever-increasing variability in chloride thresholds. Now, we're going to get back to this later, but if we try to eliminate most of the sources of variability, for example, if you remove concrete out of the picture so you don't have to worry about the pores or crevices or cracks that lie in between the steel and concrete, if you eliminate all the mill scale and pre-existing rust on the rebar by turning and polishing the rebar and making sure that there are no artifacts on the surface, and doing very well controlled electrochemical tests, you still see that there are differences in the passivation, passive film characteristics, and also chloride thresholds based on the type of solution, simulated pore solution that you use. For example, in this slide, electrochemical tests show that the passivation of rebars that are turned and polished, perfectly mirror finished surfaces, they actually create different passivity behavior. These are analytic polarization curves. Here, different passivity characteristics depending on in which environment the passive films have formed. And if you look at chloride thresholds, for example, if you passivate, for example, a turned down polished mirror surface rebar in a pH solution with a pH of 13.3, and you passivate another set in a pH of 12.4, making sure that they have very similar surface properties, no mill scale or rust through rust layers. And using electrochemical testing, you would note that the chloride thresholds that of the rebars that have been passivated in a high pH environment would be considerably higher than those that have been passivated in a lower pH environment. So the chloride threshold concept still shows differences depending on the environment, what kind of pore solution we have around the reinforcement and what kind of passivation we see. So understanding passivity and passive films become very critical in our understanding of how these systems would behave when they face with aggressive conditions. So this is what I will do in the rest of the presentation, and I will try to show this interdisciplinary, multi-scale approach to study this problem. Now, the passive films, as we will see very shortly, are extremely thin layers that form on metal surfaces. Their thickness are typically in nanoscale, so you need very special nanoscale experimental methods to actually visualize them and to analytically characterize them. So, for example, you may have to use conventional bright field transmission electron microscopy to visualize these passive films. You may have to use a dark field mode to look at the amorphous versus crystalline phases. You may use EDS to do an elemental analysis, and EELS and XPS to differentiate the oxide compositions. So we will go over these just to demonstrate what kind of information we can extract from each of these techniques and how these results or observations help us tell a story with respect to passivity and passive film. Now, in order for us to study these passive films, we have to have a way of sampling them so that we can put them under a microscope or spectral analysis device to look at them. So focused ion beam sampling, sample preparation, is a technique that has been used for a long time. I will just mention this very briefly. Most of you are familiar with this, but with respect to studying passivation, I think this is useful just to give some background. We take the rebar specimens that we want to study, we put them in the pore solutions, simulated pore solutions that we want to use to passivate them. We keep them for about in those solutions for about 2 weeks. That's basically when a stable passive film forms on these systems, and we take them out in a nitrogen purged environment so that we don't introduce additional air formed oxides on these systems, because we want to make sure that we only study the passive film. And then we purge these passive film, we purge onto these passive films a gold layer to lock these passive films. They're a tungsten layer to make sure that the layers are stable. Then you use a focused ion beam to trench out an electron transparent thick sample so that you can look at them from the side under a TEM microscope so that we can study the thin passive film. So that's basically the idea of focused ion beam sample preparation. Here we show some steps of this. You can see that this is from the top view, from the top tungsten layer. You start cutting a trench and you get deeper and deeper. And when you actually dig out most of the sample, you can now hold on to this with a sample, with an electrostatic sample holder, and pull out and put it under a TEM microscope under vacuum, so that you can look at it from the side to study that thin, very thin passive film. These samples have to be extremely thin so that the electrons can pass through to get some image and quantified analytical data. So when you do that, you can see that under a conventional bright field TEM microscope, you can actually visualize a passive film on a steel surface. This is a passive film that was formed in a pH 13.3 simulated for solution that includes sodium hydroxide, potassium hydroxide, calcium hydroxide, and so on and so forth. And you can see that here it shows that this thickness is about 5 nanometers. And if you actually look at the different types of passive films, you would note that the passive films would range from 3 to 10 nanometers. 10 nanometers probably on the high side, but let's say 3 to 5 nanometers would be a typical passive film thickness. But the thickness and the composition of the passive film depends very heavily on the type of pore solution that you use. And if you look at the dark field TEM images to differentiate how much of that layer is crystalline and how much of that layer is amorphous, you actually notice that almost all of that layer is formed of nanocrystalline particles. So you're actually looking at a crystal structure. And if you look at the selected area diffraction patterns, you would note that the film that's formed, the passive film that's formed on the steel surface, is an epitaxial relationship with the substrate, which is the steel-based plate, basically. That implies that basically the film that's forming has the same crystal structure as the substrate. But actually, in a way, the film is forming within the crystal structure of the substrate. So it is not like a flaky coating layer. It is a very well-connected layer that you cannot just peel off. This is something that's an important thing to note. X-ray photoelectron spectroscopy gives us information about the characteristics of this passive film in terms of its oxide or oxyhydroxide composition. We actually, first of all, learned that the oxide composition within the thickness of the passive film is not uniform. It is actually a layered structure where the oxide composition changes across the thickness. And if we differentiate oxides with respect to this Fe2 as an iron charge, we see that the Fe2 to Fe3 oxide ratio becomes a critical parameter. In fact, you see that, for example, deeper into your passive film, as you get closer to the steel surface, the bare steel surface, the Fe2 to Fe3 concentration increases. And we also know that Fe2 plus oxide structure is a more dense and more protective oxide structure. So the higher the Fe2 to Fe3 oxide ratio, you actually have a more protective oxide film or the passive film on the metal surface. And this is very well characterized with XPS. In a high pH environment, let's say 13.3, Fe2 to Fe3 ratio is higher than a lower pH environment where the passivation occurs, let's say in 12.5, and that difference in Fe2 to Fe3 actually helps us explain or helps us make an observation that this quantity is well correlated with the protectiveness of the passive film. You can use the same approach to study the effect of chlorides. For example, if you take these samples and you have multiple ones of these in different passivating solutions, they're all passivated, let's say 12 weeks. And after, sorry, not 12 weeks, 2 weeks, you start incrementally adding sodium chloride to see what the effects of chloride on these passive films. and let's say you add 0.1 molar chloride and you wait for a couple of days and you take a FIB sample and look at it under a microscope, and then you wait 0.2 molar, you add 0.2 molar chlorides, wait, let's say, a couple of days and take it out and do a FIB sampling and look at it under a microscope, you actually can see how chlorides interact with the passive film. And this is the conventional bright field TEM image for the passive film. When you add some chlorides to the film, but at the level that you don't expect depassivation, the breakdown of the passive film. So you do these things in parallel to electrochemical tests. You know that, for example, a certain amount of chloride would not depassivate the film, and you add that much and you look at it under a microscope, you actually see that the passive film appearing very healthy. There are no deterioration in the passive film. So the TEM imaging actually shows that passive film is not affected by the chlorides that are below the chloride threshold. But if you exceed the chloride threshold, that is the chloride threshold determined by the parallel electrochemical test. If you add more chlorides and you look at it under the TEM microscope, you actually see the deterioration of the passive film. So we can visualize the deterioration as a function of chloride content. And we also conclude that this concept of critical chloride threshold is not just an engineered property or a hypothetical property. It is actually a real concept. Although the quantification of that quantity of critical chloride threshold has challenges, this change doesn't change the fact that it's a real concept that exists. There is actually a critical chloride threshold that differentiates a passive film from a deteriorating film that results in active corrosion. Although the microscopic studies, spectral studies in nanoscale helped us quite a bit in understanding what passive films look like and what their compositions are. And I have to admit that I did not show everything that we had in the papers that we published. I highly recommend you have a look at those if you want to learn more. But there remains a number of questions that are not answered yet. For example, we understand that chlorides are doing something to break down the passive film, but what is that specific role? What is mechanistically happening? Are there any models, depassivation models, that can be used to describe this mechanism? And there, for example, the effect with ion exchange. I'll talk about these things a little bit more later. How do we explain mechanistically the effect of pH? How do we explain the concept of critical chloride threshold mechanistically? There is a concept of induction period. For example, even when you exceed the critical chloride threshold, the depassivation doesn't occur suddenly in an instant. It takes a while to fully break down the passive film, and that's sometimes called induction period. How do we explain the induction period? So that's why more answers are needed. And one of the key questions that I just mentioned is the mechanism. What is the mechanism of chlorides breaking down the passive film? Now, if you look at the literature, you actually would find a number of passivity breakdown models that have been proposed for different metals in different environments. For example, adsorption model assumes that aggressive species like chlorides attack the passive film chemically, and that basically deteriorates the passive film over time. It gets thinner and thinner, and it disappears after a while. Ion exchange model assumes that chlorides penetrate into the passive film. They basically go through the passive film to reach the metal surface, and during this process, break down the passive film and cause corrosion initiation. In the point defect model, chlorides do not penetrate into the passive film. They do all their work on the surface by basically creating iron vacancies. They take iron atoms out of the surface, they create iron vacancies. These iron vacancies travel through the passive film, reach the interface between the steel and the passive film, and they create these voids, and those voids basically merge after a while, and they create conditions for the breakdown of the passive film. So that's called the point effect model. So how, which one of these would be the answer is a good question. Unfortunately, experimental techniques fail to answer these questions at this scale. So you have to rely on atomistic, molecular, and sometimes quantum mechanics calculations to get information at that scale to answer these questions. We have done both reactive transfer, reactive force field, reactive force field molecular dynamics simulations, and then the functional theory simulations to answer a lot of questions like this. Today, I'm going to focus on reactive force field molecular dynamics simulations to answer some of the questions that I described in this presentation, but more information can be obtained for other questions and other inquiries in these papers. There are a number of additional ones that I can provide you if you contact me later. So if you think about, for example, a passivating system, and in this case, because these simulations are extremely time-consuming and computationally expensive, we have to make some simplifications. For example, we are looking at a perfect crystal iron structure instead of a defective steel structure, which is what you would have in normal in real life. A very small domain, of course, because we have to limit the computational expense. We expose them to a high alkaline, in this case pH 13.5 sodium hydroxide solution, and see if the molecular dynamics simulations would create a passive film. And it does. You can see here that the oxygen atoms are penetrating into the crystal structure of the iron domain. And you can see that the iron domain crystal structure remains the same, but you form different forms of iron oxide and iron hydroxides. So that epitaxial relationship that we have seen under TEM microscope actually is confirmed here. The film is not like a flaky film that forms on top of the steel metal. It is actually in a real connection with it, so it's organically connected, and organic, the word there is not in the literal sense. And if you look at the composition of those oxides, you can actually look at the distances between the atoms, oxygen and iron atoms. You look at the pair distribution function plots to identify what kind of oxides you're forming. You actually confirm the observations that we had from, like, say, eels or XPS analysis to that gave us a layered oxide structure where the inner layers are mainly in the form of Fe2 oxides and outer layers are in the form of Fe3 oxides, and between there's a transitional period. And that Fe2 to Fe3 ratio increases to go deeper into the passive film. And that's basically just to remind you the XPS data that we had before. Now, we can also use molecular dynamics simulations to look at what chlorides do. So you take a passivated system to start. This is a system where you actually created a passive film through molecular dynamics simulations. That's your starting point. And you expose that passivated surface to that same electrolyte pore solution, but this time with some sodium chloride in it. So the chloride atoms are shown here in black circles or spheres. You can see that the solution has sodium chloride, and you do the simulation at different levels of sodium chloride to see the effect of the concentration of the sodium chloride. And if you do this, you see some interesting observations. You make some interesting observations that help you answer some questions that we have identified before. first of all, we see actually chlorides cause corrosion. You can see those purple iron atoms are extracted from the main body of the steel, and they actually join the solution, so they became corrosion products basically. So you can see corrosion, active corrosion at certain chloride contents. And if you look at the black spheres, which are chloride atoms, they do not necessarily get into the passive film. They do their job on the surface. So in a way, this gives us some indication that the mechanism might be more like the point defect model than the ion exchange model. So this is an important conclusion that we can, or observation that we can make from molecular dynamic simulations. And interestingly also, when chlorides extract these iron atoms and create these defects in the oxide structure, they actually take those iron atoms into the solution and they release them so that the iron actually oxidizes further in the solution to create corrosion products. But the chlorides release back into the solution and they go back to the surface and they do additional damage. So in a way, we can define this process a catalytic process. So chlorides act as a catalyst in this process. And if you also look at the pair distribution functions, you actually can see that transition from iron 2 plus to iron 3 plus, to more protective oxide structure to less protective oxide structure as the chlorides do their job. So this is also something that we can capture in molecular dynamic simulations. So what do chlorides do? It is, you can actually zoom into different steps, in time steps of this simulation, and you can see how chlorides actually help extract these iron atoms from the oxide surface and create these iron vacancies. So the process requires, first of all, some local acidification. The OH pairs attach themselves to some of the iron atoms. Thermodynamically, this is a stable process, a favored process, and they try to pull those iron atoms from the oxide, but that bond is not strong enough to dissociate the iron atoms. You need additional chlorides, but that can only happen when you consume enough hydroxyl pairs so that chlorides can form these FeOH chloride 2, FeOH Cl3 kinds of types of phases that are actually able to extract those iron atoms from the surface of the oxide or passive film, and create iron defects. So this 4-step process is very well described in materials and degradation paper here I show you, and I encourage you to have a look at it to see a better description, a more detailed description. But to summarize, I want to highlight that this process of creating these iron defects, iron vacancies, or extracting iron atoms from the surface is associated with local acidification, consumption of the OH pairs on the surface first, and then dissociating the iron atoms. So if you have more OH, you would need more chlorides to do this kind of damage, create the vacancies. So that, in a way, explains why the effect of higher pH environments create passive films that will depassivate later or require more chlorides to do that. It explains induction period because these iron vacancies that are formed has to travel through the passive film to actually get into the steel metal oxide interface to create that depassivation breakdown process. You need, as I said, higher level chlorides to create iron dissolution at a different pH. And again, I will repeat this here, even the molecular dynamics simulations show that the concept of critical chloride threshold is a valid concept. In order to dissociate these iron atoms, create iron vacancies, you have to have a certain level of chloride content in your solution. Otherwise, this doesn't happen. So the concept of critical chloride threshold is also validated in these simulations. And here you can see this iron vacancy formation. Those iron vacancies basically travel toward the metal oxide interface, and they basically break down the passive film that way. So the molecular dynamics simulations suggest the point effect model as the mechanism that defines the chloride-induced depassivation process. There's a 1992 paper, it's a very good paper by David McDonald, who actually proposed this point effect model for depassivation and clearly described the steps how this happens. As I described in the molecular dynamics simulations, you create some vacancies, in our case iron vacancies. Those vacancies travel, they accumulate at the metal oxide interface, they merge to create these bonded zones. Then you basically thin the passive film, and that passive film, because it gets thinner and thinner, breaks, you get the breakdown of the passive film. For more information, I highly recommend you to have a look at this paper. So I have shown you a number of studies spanning a large scale from atomistic to macro scale, electrochemical scale. And I tried to show you that thanks to this interdisciplinary work that bridges the length scales from atomistic to macro, we have developed a good understanding with respect to the passivity and chloride depassivation of steel and concrete. In doing so, we actually had to collaborate with a large number of researchers coming from very different backgrounds. We worked with nuclear engineers, chemical engineers, material scientists, surface scientists, corrosion scientists, microscopy experts. It required, and of course, computational material scientists, it required a very large group to deliver this kind of conclusion or this kind of knowledge that spans a very large length scale. We also showed that the concept of critical chloride threshold is valid, even at the molecular scale. So there's no question in our minds that this is valid. However, there's also this practical aspect that the variability we observe in macro scale makes the practical use of the chloride threshold concept a challenge when using it specifically for service life modeling exercises. And I'm going to highlight this very carefully. Chloride threshold concept is a valid concept, but with respect to using it for service life modeling purposes, there are some challenges. And we, some of us who are listed here, Professor Angst, Carolyn Hansen, Alberto Sagüez, Mette Geiker, we were talking about this challenge in one of the Gordon conferences in Ventura, California. And we decided that we needed to write a paper to maybe give a different perspective and to open a maybe new framework of looking at things in terms of service life modeling. So we wrote this paper, this recent paper came out last year, Beyond the Chloride Threshold Concept of Predicting Corrosion of Steel and Concrete. And here I want to make a pitch. I want to highlight that although the 2T is two-stage model that basically is based on two independent stages separated by a well-defined chloride threshold, has been very useful in many things. It has not been as useful in doing service life modeling exercises that covers the service life of reinforced concrete structure with respect to corrosion. Let me talk about this a little bit. For example, if you look at a steel embedded in concrete, from day one, the steel starts experiencing electrochemical processes. It actually starts passivating. So there is some corrosion current that creates the passive film. When it is passive, you still have some corrosion current there, although very low, to maintain the passive film at a healthy level. So that period was initially described as initiation stage, but this doesn't change the fact that when chloride content increases, the passive film may break down, but it may repassivate even at very high chloride contents if the conditions reduce the corrosion rates to very low levels. And this might happen at low moisture cycles, for example. Now, in this plot, for example, at point A, you can see that there's a passive region. Chlorides increase over time, maybe exceed the threshold level, so you get some active corrosion, but maybe the moisture content drops. Although chlorides are high, you might see a very low corrosion afterwards. And these cycles of passivation and repassivation, activation and repassivation might occur deep into the service life of the structure, many years after the initial breakdown of the passive film, where you would define a two-stage model, the start of the propagation period, you might have dormant phases where the corrosion current density might be very low. And different parts of the reinforcement might experience different behaviors. So it is important to understand that instead of separating or instead of defining the service life of these systems as two independent stages, if we keep the framework there, these are continuous systems. From day one, steel experiences some electrochemical processes until the end of its service life, and we focus on the corrosion current density or the corrosion rate rather than the initiation and propagation stages. And we look at the problem from a continuous point of view from day one. By monitoring the corrosion current density or corrosion rate, we might have a better framework to look at the service life modeling of these systems. So in that paper, we propose a renewed focus on measuring and or predicting I-core, which is the corrosion current density or corrosion rate, which has the potential to take us to the next level with respect to service life modeling of reinforced concrete structures. In this, by no means I'm trying to say we should get rid of the concept of critical chloride threshold. That's actually, that has been a useful concept for many reasons, but for service life modeling purposes, we might have, we might need a renewed focus, and this is a pitch that we have made in that paper. I really appreciate your time in this talk. I'm looking forward to answering your questions and meeting each one of you in person in the future. Thank you for your attendance, and I'm looking forward to talking to you soon. Thank you.